The IFBF is one of the biggest events in the flow battery industry. Our delegates come from across the flow battery industry, covering both the technology and the applications. We look at research, development, design, as well as economics, applications, marketing and investment. We're very fortunate to have amongst our many friends Professor Maria Skyllas-Kazacos. Maria is one of the most knowledgeable people in our industry. Her drive to develop the vanadium flow battery has led to the creation of this vibrant and exciting industry. I spoke to her earlier this morning.
Hello everyone, and thank you Anthony for all the work that you and your team have done to put on this showcase. Over the past 10 years, the International Flow Battery Forum has worked so hard to raise awareness of flow batteries around the world, and they've always managed to design an excellent program that brings together industry, academia and government organisations to discuss the important issues facing the energy storage sector, especially with regard to flow batteries. This year, we're all confronted with a great emergency that has prevented us from attending in person, but it's wonderful to see that even when we can't travel, we can still work. We have another exciting session today, but we're all looking forward to the next full IFBF that will be held in Düsseldorf in January. We all hope the travel restrictions will have been lifted by then so that we can meet and hear about the latest developments in flow battery technology and applications. Until then, may you all stay safe and well, and go with the flow.
Thank you very much, Maria. Could I just ask you, just to add, what was your most important recollection of yesterday's discussion?
Well, actually, there were a couple of things, as I must say. I was really impressed with the work that has been done to increase the supply of vanadium and the leasing arrangements that are being put in place. And I think that's going to make a big difference to the upfront capital costs of vanadium flow batteries and also help to stabilize the prices and the supply of vanadium into the future. And I think I really congratulate all the companies that are working hard for that. But I was also really amazed to hear about this new emerging energy storage market for long duration batteries. And hearing about the need for 10, 12, 14 hours of storage, which I think, for this new data storage market. And from what I can gather, it's really only flow batteries will be able to meet the requirements in the near to medium term. So that was really exciting for me.
Maria, thank you very much. It's great to talk to you again, and we look forward to seeing you at the next IFBF. Thank you.
It's a pleasure, and I look forward to hearing all the presentations today as well. Thank you again, Anthony. Thank you, everyone.
Yesterday, we heard about the role of longer duration storage in the energy policy of Europe and in the USA, with inputs from Patrick Clarence, Imre Juk and Nikki Herbert. We heard from manufacturers and suppliers and users about the applications and benefits of flow batteries. Adam Roussel of Renewable Energy Aggregators and Kenneth Davis of Birch Infrastructure outlined the latent need for enormous long duration energy storage and the requirement for hyper factories to ramp up demand for some serious large scale battery production. Today we have two sessions again. We'll hear about some more applications of flow batteries and the latest developments. You've probably found that there is a questions tab on your screen. Please submit your questions for our speakers and we'll group these for each presenter. The recording will be made available through our website later in the week, and we'll also make the slides available. And the latest edition of the Flow Battery Map has been published on our website. If you downloaded it yesterday, please check back as it's already had a couple of additional projects added and some more sponsor details included. Our first speaker today is Tim Harris of Redflow. Tim has worked for many international companies and is now CEO of Redflow, an Australian flow battery manufacturer. Tim was formerly with Chorus, New Zealand's largest telecoms infrastructure company, and he's also worked for BT, the British multinational telecommunications company, which operates in 180 countries. I'm sure that Tim wants to tell us about Redflow's customers in the telecoms markets and how his company's flow batteries meet their demanding requirements. Redflow participated in our first IFBF in 2010, and it's good to have you back with us again. Although, because it's now well past midnight in Australia, this is a recording of his presentation.
Redflow Energy Storage.
Hi everyone, I'm Tim Harris, the Managing Director of Redflow, and I'm really delighted to be presenting today at the International Flow Battery Forum web conference. First of all, my congratulations to the team with Anthony and the rest of the team for kind of pulling this together in what is kind of clearly challenging times for our market and for our customers and the global economy. What I'd like to talk about is just an overview of Redflow, where we are and what we're doing and where we're focused, and then start to talk about an individual case study of what we've done for an off-grid telco customer for us here in Australia. Firstly, a little bit about Redflow. We're headquartered here in Brisbane, Australia. We have a wholly owned company manufacturing facility in Thailand, and our core purpose is we design and manufacture zinc bromine flow batteries. We design one 10 kilowatt hour zinc bromine flow battery, which is modular in approach. Our target markets are in the telco, commercial, industrial, remote area power systems and high-end residential space. And from a geographical point of view, our major focus in Australia and New Zealand, certain markets in Asia, and also we're seeing tremendous growth in places such as Southern Africa. I'll talk a little bit more now about some of the high-level technical aspects of our battery. Our battery is a 48 volt DC nominal battery with a maximum 10 kilowatt hour energy output per daily cycle. The dimensions were roughly 850 millimeters length, 800 millimeters height and 400 millimeters wide. We weigh about 240 kilos with electrolyte and have an energy efficiency of 80% DC to DC max. Our power rating is 3 kilowatts and 5 kilowatt hour peaks. We've designed the battery to be modular in approach, so we can have deployments of single batteries up to multiple batteries depending on the requirements of the customer. One of the key aspects about our position and our strategy is decreasing the lifetime cost of using our battery. Now, clearly we believe that we've got an inherent competitive capability because we have higher energy density than vanadium or lead acid. And our tolerance for high temperatures means that our customers don't require air conditioning OPEX for those target wall climates that we're in. The next 12 months are going to be very important for us. We're finalising development of our Gen 3 battery, which includes a significant redesign of our stack, and that's going to enable significant further cost reductions as we ramp up in terms of economies of scale. In the future, we see considerable opportunities for offering late life refurbishment and recycling of the chemical components of our batteries at the end of life. And clearly we're also targeting, as we go through with a significant ongoing investment in R&D, improved performance to increase the customer dollar per kilowatt hour benefits. One of the things I'd just like to dwell on is just talking about our battery performance. So Redflow has been part of the Australian Federal Government funded testing of multiple batteries that have been conducted for a couple of years. After a couple of challenges with our previous manufacturing relationship, we've had one of our Thailand manufactured batteries on test since February 2019. That battery is cycled close to twice a day, and the recent report that came out from the ITP that's running this program for the Australian Government showed our state of health at 100% after 600 cycles. Further to that, further analysis that we have done looking at the battery at over 700 cycles again shows no degrade in performance. That when you compare with other lithium batteries, I think is a very strong point of evidence in terms of the benefits of flow batteries. So one of the things that we've been doing over the last couple of years at Redflow is probably narrowing our focus in terms of those markets, geographies and applications where we think we are best suited. And there's a number of those that we think are really pertinent and where we are seeing kind of strong traction. One is in off-grid type environments where the power system is relying 100% on diesel generators to power that site. But we also see strong opportunities where there are weak grid environments like South Africa, where energy resiliency is absolutely required. We've also had deployments in 100% off-grid type deployments and also remote kind of power systems. So look, from our perspective, we think there's a tremendous opportunity across a range of markets for Redflow, but really we think that focusing on some of these key applications and markets is a great thing for us to do at this stage. From a target market perspective, look, we really focus on those markets that have energy-focused applications, require frequent cycling, and especially those environments that they have warm climates that rapidly degrade other battery chemistries. Look, a lot of our present focus at the moment is on the telco space, and we've made some tremendous progress with some of the world's largest telcos over the last 12 months on that basis. Clearly, power costs in the telco space are a major cost factor, and the size of that market, we think, presents material opportunities for us to drive volume. As you can see on the slide there, there's about 4 million base stations globally, growing at a rate of about 5%. But a lot of those new deployments are actually occurring in areas that have weak or no grid type environments. And given our form factor and our size, we think that it's a market that we can absolutely play in. So look, we're engaged with a number of telco and tower operators that have about 70,000 towers under management, and hopefully once we get through this kind of COVID situation, we can start to drive more material sales in that area. I think the other thing that we see in the telco space is the real focus on efficient energy management and the emergence of power as a service type models that's starting to emerge in some countries. I think when you combine that with a lot of renewable energy commitments that a lot of the telco global operators have, we think this presents a tremendous opportunity for Redflow. So now I'd like to talk about one of the recent deployments that we've done in the telco sector. This is a deployment that we've done with a company called Optus, which is Australia's second largest mobile and telco operator here in Australia, which is owned by the Singtel Group. We started with engaging with Optus a wee while ago that we're really looking for new solutions to power their base station sites in remote areas. And so one of the target sites that we identified was a base station site in the Daintree Forest. The Daintree Forest is a conservation protected area, so it's highly sensitive to environmental issues in far north Queensland here in Australia. The site was previously running on diesel only, so running diesel 24/7. And for this site, there was no potential to put solar in there due to the restricted land and forest canopy. So we engaged with management from Optus over a number of months, and they selected our battery because of a couple of reasons. One is because of the sustained energy storage capacity that our battery has, the tolerance of warm temperatures, the fact that through our battery management system, we can remotely monitor the battery and optimize the battery, and clearly because of some of our environmental credentials as well. So the solution there that we've delivered for Optus in that site consists of 6 of our batteries, so 60 kilowatt hours that sits alongside the diesel generator. The diesel generators then power the site and charges our battery, and you can turn the diesel generator off while our batteries are discharging. What we've also developed as part of the solution is the ability to have these batteries charge and discharge on a sequential basis. And that's managed through our Redflow battery management system, and also utilises our new standby power supply mode that enables us to park batteries at 100% charged to use those when you need to. So that site was, we deployed our batteries there in April 2019, and those batteries were commissioned a month later. So since commissioning, our batteries have had energy throughput of about 7.4 megawatt hours, and according to our calculations, we've achieved a 70+% reduction in those diesel generators working. So not only does that have benefits in terms of commercial benefits, because getting diesel to that site is a huge logistical challenge, and it's also very costly, But that also has a major environmental impact in terms of the reduction of that diesel and that CO2 emissions from reducing that diesel generator time by 70%. So we're speaking to this operator about some other sites, but we think that's a key reference deployment that has applicability to a number of our telco customers and opportunities that we see on a global basis. Look, I think from the customers that we speak to, there's an awareness of flow batteries, but because we have quite a different form factor at our 10 kilowatt hour type battery, we do have to talk to customers in terms of some of those spaces that we can play that other flow batteries might not be. I think from where I sit, especially talking to a lot of our telco customers, power costs and resiliency is a huge part of their business. So our ability to come in there, I think, and offer a solution that is a little bit different from what they can currently get, I think we're pushing against an open door rather than a closed door. I think the important thing for us is to actually show and demonstrate flow batteries working in the field and the target applications and environments that we want to be successful in. So we've got about 90 deployments now that are active, and that's grown by about 40% over the last 12 months. And we think that's the major proof point that we can point to our customers to say, look, our batteries are working in the field, they're doing exactly what we said they would do, and look at all the benefits that they can generate from our batteries versus potentially a lithium or lead acid solution. Look, there's no doubt that COVID's had an impact on our business. At the start of the year, in March, I was in South Africa, and we're pretty excited about a major opportunity for Redflow in that market in the telco space. Then literally 2 weeks later, the country shut down in South Africa, but elsewhere because of COVID. So look, it has affected our business. We're still continuing, we're still engaging with our customers, and we're still generating some orders. But we do recognize that it's going to take some while before we get to kind of business as normal. And one of the key things we are doing that I think I spoke about before was focusing on our Gen 3 product. Now, that's a significant advancement in terms of our stack design and manufacturing, but it really sets the platform for a volume manufacturing business for us because it makes it much simpler to manufacture at a much lower price point. So that's one of the key things that we're going to be focused on with a target customer trial by the end of the year. So look, we've announced a capital raise a couple of weeks ago to really, because of COVID, to get us through the next 12 months. We're really going to be focusing on maintaining those relationships with our customers, getting some further orders, I suppose, hopefully as markets start to lift some of their restrictions, and also focusing on that Gen 3 product. And so the Gen 3 product for us is really the platform for a volume manufacturing business for us. So it's very important that we start to execute on that, and that's going very well, and we're very confident about meeting that December 2020 customer trial. Look, I think on an overall basis, the overall element around sustainable renewable energy is becoming more and more important in terms of the eyes of our customer, and that's a commercial decision, but it's also, I think, a strategic decision. I mean, let's have no doubt that the commercial components of an energy storage solution are at the forefront of a lot of our end customers' minds. But you'd be surprised to see the emerging concerns coming about environmental credentials, what happens at the end of life, what can we do to extend the life of your battery versus other solutions which are essentially disposable. So look, I think that is an emerging thematic that's starting to come through in discussions with our customers. You have to make the commercials work. But I think as a flow battery community, we have an absolute message that we can take out to our customers there that provides a really key point of differentiation.
Redflow Energy Storage.
Thank you, Tim. Our next speaker this morning is Dr. Jonathan Williams of Marine Southeast. Jonathan has been CEO of a marine sector consortium, Marine Southeast, since its launch in autumn 2005. He's led its development to become a catalyst for marine business investment in innovation and diversification. Marine Southeast is now widely recognised as a leading European marine cluster, centred on the world-class business and research capabilities of a UK Solent region. Jonathan was previously Chief Executive of Marine Tech South, a research management and technology transfer business. He's a specialist in innovation, so I've asked him to speak to us about maritime applications for flow batteries. Welcome, Jonathan. Please turn on your microphone and over to you.
Thank you very much, Anthony, kind words. Yes, my name is Jonathan Williams. I run Marine Southeast. It's a non-profit, and we exist to form consortia which can find solutions to some of the really pressing problems that are and challenges facing the ocean industries today. So I'm going to talk briefly around a few projects that we're running at the moment, which are relevant to flow batteries, and I hope they're of interest. But the first place to start, of course, next slide, please, is someone got the, yeah, is the first place to start is why why this is an important challenge and why this energy transition is taking place. And the one reason, which doesn't need me to say any introduction, is of course the decarbonisation agenda. And the marine industries have been pretty slow off the mark, actually, in picking this one up. We're now under the cosh, and so there's an action plan now to move pretty quickly. The light green bars on this diagram on the left show the proportion of energy use which is projected to come from renewable sources, including using batteries as a store, as well as other energy vectors. So exciting growth opportunity. But it's not just carbon. There's also a massive air quality issue for marine. Some of the numbers here on the right-hand side of the slide are frightening. So the pressure is on to address that one, and the opportunity to be able to bring your ship into port, for example, under all electric propulsion to avoid the sort of scene that you see on the picture here on the right of the slide is clearly very much in demand. So we believe that that batteries have a really important role to play in addressing both of these challenges. Next slide, please. So maritime electrification, where are we on this? And the answer is it's already happening. And initially we've seen all electric vessels operating on short ferry routes, for example, like this one I'm showing on the top right of the slide here, 2.5 nautical miles crossing, all electric, operating between Denmark and Sweden. But there are many other opportunities as well. So, for example, hybrid ferries on longer crossings, which we currently don't think are realistic to operate on all electric, but the ability to switch on to all electric for certain parts of the transit could be very attractive, could be game changing actually, for some operators. There are also smaller vehicles and vessels that we can target. So the sort of vessels that are operating in a port, currently producing emissions, which we can electrify. And those are generally smaller and therefore very manageable, very good candidates for electrifying in the short term. But what we put on the vessel is only part of the picture, because for every battery on a vessel, you've got to have recharging infrastructure in the port. So at least half of our activity is now focused on ports and what they need to be investing in order to have the infrastructure in place. And part of that infrastructure has to be onshore batteries. We, for various reasons I'll explain in a moment, think that flow batteries have significant advantages over other technologies like lithium-ion. Next slide, please. So first project is this one called PESO, Port Electrification Project, stands for Port Energy Systems Optimization. And the key point here is that when a vessel comes into port and connects up to your electrical system to recharge, that's a massive load that suddenly appears. It could be tens of megawatts. So we need the infrastructure to cope with that. And batteries are clearly part of that. And the PESO project is looking at what kind of battery management systems would optimize the use of that battery so that you can make best use, for example, of when you buy your grid power. We know that batteries are going to be really important economically for ports to address this challenge, because another project which is being led by Swanbarton has looked at this point, and we can see from that work that flow batteries have a significant contribution to reducing the capex, for example, to reduce the need for grid reinforcement, which can be a crippling cost for ports, but also allowing you to optimize your procurement of power from the grid. And the reason we think that flow batteries in particular have a massive opportunity here is because a number of reasons, but one of the main reasons being that with a flow battery on land and a flow battery in the ship, you can recharge hydraulically. And for vessels like ferries, which need really rapid turnaround, that can be a really important factor. And also because their ability to scale up at low cost means that for ports, it's an attractive investment profile. So next slide, please. So that's the port bit. In terms of how we put flow batteries on a ship, we have another project called FlowMar, and this is showing or answering the question, is it realistic to put a flow battery on a ship? How do we do it? So we're working with a local company that actually designed this vessel you see on the slide, which is a hybrid vessel. And they're asking the question, well, what would such a vessel look like, or a similar vessel look like, if it had a flow battery and was operating all electric? And we're starting to think that for routes of anything up to about 100 nautical miles, it is realistic to have a flow battery providing all electric propulsion. So we think that there's the project is only just started, but we're very optimistic that this will really show how flow batteries can be used. We also can already see significant benefits over lithium ion, which is the main, that's the main contender, and it's currently the technology which is most widely used in marine, with companies like Corvus, who are very, very active in this field. And the reasons are, one I've already mentioned, faster recharging, but also the longer battery life we think could be critical. If you've got to dry dock a ship to change out a massive lithium-ion battery pack, that's extremely expensive and very inconvenient. And if we can avoid that, offer solutions that avoid that, then that's going to put us in a significant advantage. Next slide, please. So that's the two obvious ones. This is a slightly left field opportunity, which I thought I'd mention because it just shows the breadth of opportunity which the marine industry has offered to battery manufacturers. What this slide is about is the fact that in the coming years, we're going to see a significant expansion in what we loosely call offshore infrastructure. That is to say, to support activities like offshore aquaculture and offshore wind farms, which are both growing exponentially at the moment, we're going to need the infrastructure to support those facilities. And we think that we're starting to think about how we build that. We're involved in leading an activity in a project called Periscope, which is a Scandinavian-led project to explore this particular requirement. And I won't go into detail, but what I will just point out to you is that if you look at that picture of the floating wind turbine in the top left of the graphics, what you need to understand is that those yellow cylinders which go into the water, there's a significant amount of that below the water. You can't see it, but that creates a big volume of space which can be available for electrolyte tanks, which would contribute to the stability of the structure. So we can see a future where we have offshore infrastructure with a significant amount of flow battery energy storage, providing a whole range of services for the companies operating these facilities for inspection, maintenance, repair, surveillance, security, and so on. So just by way of conclusion then, next slide. Couple of conclusions. The first one is that we see exponential growth in demand for maritime batteries generally. It's happening now already. In ports, it's going to happen in the very near future. Well, it's already started. And for offshore use, that's going to come follow up in future as well. And we think that within that market, maritime flow batteries could steal a march really on the competition for reasons that I've already explained: rapid recharging, more flexibility in the layout of your vessel, and the longer life. So I hope that's been of interest. Happy to take any questions. Thank you very much.
Thank you, Jonathan. Andy, do we have any questions, please?
Hi, yeah, we do. We've got one question regarding what benefits would a flow battery have over a hydrogen fuel cell? Are you happy to take that one, Jonathan?
Absolutely, absolutely. No, it's a very good question. One that we're quite often asked, actually, because the hydrogen fuel cell option gets quite a lot of press these days. And I'm not going to knock it. It's got its place in the spectrum of solutions which we ought to be looking at. I think we see that the hydrogen fuel cell option may become a bit more of a range extender option. So we can see that there could well be interest in electric vessels, all electric vessels, but with a proportion of the energy capacity provided by some hydrogen storage on board to extend the range that you can achieve with all electric. So I think these technologies, I don't see them actually as competing so much. I see them as being integrated into systems which can operate to give the solution that the market needs.
Jonathan, thank you very much. I think that's a good point to move on. We heard a lot from you about the environment and sustainability. Our next speaker, Jim Stover from VRB, is going to also speak about the environmental credentials of flow batteries. Jim's VP of Business Development at VRB Energy. He's no stranger to flow batteries in the energy business, as he was previously Vice President International Operations for Prudent Energy and VP Asia for Northern Power Systems and the Distributed Energy Systems Corporation. Welcome, Jim. Please turn on your microphone and over to you.
Great. Hello, and thank you for the introduction, Anthony. Can you hear me correctly on my microphone here?
You're absolutely fine. Please go ahead.
Perfect. Great. Well, you can go ahead and advance to the next slide. I'll give a quick introduction on what's up with VRB Energy, and then I'll focus on the sustainability and environmental issues. First off, quick background on us. Our immediate parent company is HPX High Powered Exploration, a mining company that's focused on new energy economy metals, things like vanadium, as well as cobalt and nickel. The parent company of HPX is a group called iPulse out of France that's focused on pulse power technology. We're all led by a gentleman named Robert Friedland, who's a fairly well-known independent mining executive, and he's chairman of our board. He saw the potential for vanadium back in 2016, and that's when HPX came and acquired VRB Energy, which was formerly known as Prudent Energy. Our technology, you see on the top center of the slide, our 5th generation of stack. We're actually at work on our 6th generation of stack. So a tremendous amount of effort from the R&D team over the past decade or more. A lot of things you don't learn until you do them and can get your hands on them and improve and iterate. And we've had a tremendous amount of operating experience with our systems, and it continues to advance as we go. We have about 30 megawatt hours deployed and in construction right now of systems, and I'll speak about that a little bit more if we go to the next slide as well. So I'll start on the right, on the markets side. I mentioned 30 megawatt hours as our installer in construction. We're actually, we haven't issued a press release, but we've actually just signed a project in the north of China for 2 megawatts, 8 megawatt hours. And this is at a location that is looking to be one of the 100 megawatt class project locations in China as part of China's overall efforts to use vanadium flow batteries to integrate more renewables in the north and the northwest of China. I also have a quick outline, an outline of the U.S. here as another market area of focus for us. We're engaged with a number of major developers, one of whom keeps pushing us for 8 and 10-hour storage projects. I think Kenneth did a good job hitting a couple of things yesterday, Kenneth from Birch, about the need for longer and longer duration storage for data centers. We're seeing this also in the capacity markets, and as renewable penetration increases, that's really a market demand or a market driver. So that works well for us and for flow batteries in general. So I'll do this backwards. We'll go to the left side of the slide. And the bars that you see are a comparison between our systems and lithium systems on a 4-hour basis and an 8-hour basis. And as you can see, on a 4-hour basis, we're close on cost, on CapEx, which of course is what everybody asks about. But of course, what really matters to the financials and the bottom line is the levelized cost. And as you can see, we have significant advantages at 4-hour duration systems, assuming 1 cycle a day. By the way, that same developer I mentioned before is pushing us for 1-hour systems that they want to cycle 6 or 7 times a day, and that durability or the throughput that we can offer is another area of advantage. So it's not just the 8-hour, 10-hour systems where flow batteries can stand out. It's also that high cycling type application where the durability and the long life really matters too. But on 8 hours, on the right-hand side, you see those 2 stacked columns, comparison of lithium and our VRB energy system. Clear advantage on CapEx, and that's because of the low marginal cost of adding electrolyte and tanks, as well as a significant advantage on levelized cost over a 25-year project. Okay. On to the next slide, and environment and sustainability. All right, so I thought this is the last slide I have. I thought I'd put this up as a way to frame the discussion, and happy to take questions from you as Anthony can moderate. We start just maybe reframing things for folks. Vanadium comes from many different sources, and one that is a vast untapped potential is waste sources. A lot of these are petroleum waste sources or petrochemical waste sources. There's some sources that are already in landfills that can be utilized. A lot of these waste sources can have 2, 3, up to 10%, 40% or more vanadium pentoxide contained. So the ability to take, at the beginning on the sourcing side, and take a waste material and then extract the vanadium and use that in a vanadium flow battery where we're creating an electrolyte that never wears out is a tremendous environmental benefit when compared to the lithium-ion battery life cycle or ecosystem, where there isn't yet, where there are questions on the sustainable sourcing side of things when you talk about the, metals like cobalt, and when you think about recycling at end of life, and these systems degrade and would need to be replaced after about 10 years or so. If that material is not recoverable economically, then it has to be landfilled. So from the beginning to the end of life here, we have a much more environmentally friendly and much more sustainable supply chain. So multiple layers here, right? I'll get back to the slide. Waste sourcing, the example I gave is, oh, no, I'm sorry, Anthony, stay on the same slide. Yeah, the example I have here is about 2 million tons prevented from being landfilled, and that's just various type of waste ash or catalyst material. That could yield 20 gigawatt hours of storage. So big numbers, and we as a vanadium flow battery and flow battery industry need to think in terms of these big numbers, because the numbers are enormous, and we need to be able to scale up. We will scale up very well. There's plenty of vanadium. There's plenty of cost reduction that can be had on the non-vanadium side of the system, as well as on scaling up the vanadium supply chain. So we have a lot of cost reduction that we can offer going forward the next decade or more, and that's a very good thing when we see developers asking us to scale up our production. The vanadium commodity is an asset, right? So it lives in the electrolyte. The vanadium pentoxide itself as a commodity doesn't wear out, and you can either reuse the electrolyte in another flow battery, probably at higher density as we improve things over time, or the underlying commodity could be extracted back out for use in other industries. And as was discussed yesterday, also with Kenneth and with Mikhail, there are ways that you can look at leasing this material because of the underlying commodity asset value. Okay, so final point here on the right-hand side of the slide, I showed a snapshot of what a battery looks like in terms of the proportion of vanadium electrolyte and the non-electrolyte side of the battery. Depending on the duration, of course, this changes, but if we were to roughly say that 60% of the battery is vanadium electrolyte and 40% is the stacks and the pumps and the controls, that's a tremendous basis from which to do leasing and capture the financial benefits of that electrolyte that is composed of an asset that never wears out, a commodity that never wears out, and that can be reused or recycled almost indefinitely. So when you look at, again, the comparison to lithium-ion batteries, from the beginning of the sourcing through to the end of life and recycling or reuse, we have tremendous advantages. I did also want to point out one thing. I think it was Anthony that had mentioned there's a recent research report out of a university in Sweden that talks about the manufacturing intensity of lithium-ion battery gigafactories. And I believe they estimated somewhere between 50 and 60 kilowatt hours of energy input for manufacturing of a kilowatt hour of lithium-ion cells. And we did a quick calculation internally looking at electrolyte and non-electrolyte. And we came up with about 25 to 30 kilowatt hours of energy input for manufacture of 1 kilowatt hour of vanadium flow battery. So looking at that, that's something where we haven't explored it deeply, but it appears that we have a 2x advantage there as well. So yet another benefit in terms of sustainability and the environment. Do our customers price this in right now? Well, it gets priced in, it gets evaluated in terms of the recyclability of the electrolyte, in terms of the leasing of the electrolyte. I think those are all very important advantages that we have and that we can utilize to even greater effect as we scale up and build the industry out and have greater and greater volumes of electrolyte and vanadium flow batteries out there. And I think the recycling piece is one that's often overlooked by the current developers and utilities that are installing lithium-ion batteries, but is going to be more and more significant. In fact, in California, we're hearing that some of the utility RFPs will have requirements for end-of-life disposal or recycling included in proposals in order for them to be accepted. So I think we'll see that coming quite soon across the marketplace in many different geographies.
Thank you very much, Jim. Andy, we have a number of questions coming in. Would you like to choose an appropriate one on the topic of environment and sustainability, please?
Specifically on environment and sustainability. Okay. We've had a few questions about the environmental issues. In fact, unfortunately, I'm struggling to find a specific question on that. Sorry, Anthony, I can't find one on environment and sustainability in the list. There have been some questions on in terms of VRB manufacturers, what are the differentiators between different manufacturers? What scope is there for people to differentiate with the technologies?
Thank you. Jim.
Well, I'd be happy to answer that, at least from our perspective. On the electrolyte side, there are certain things that can be done in terms of the specification and the chemistry of the electrolyte, and more importantly, the processing that is done to capture the vanadium pentoxide from some of these waste sources. So there's a tremendous amount of innovation that can be applied there, and there's more room to run in terms of improvement of that processing and the recovery of the waste materials into vanadium pentoxide. On the non-electrolyte side of the battery, the key elements are the membrane materials, bipole materials, electrode materials, and actually across all three of those, we've developed in-house materials. So instead of taking things off the shelf that were previously used for fuel cells or other applications in the past, we're specifically engineering these materials to be optimized for flow battery in terms of ion exchange, as well as durability and cost performance. So there's a lot that goes into the material selection, material development. There's still a tremendous amount of improvement that can be had there. And then the manufacturing as well. There are a lot of improvements that can be made as we scale up manufacturing and increase automation in the overall manufacturing process.
Jim, thank you very much. We must leave that the debate there for the time being, but I do hope that we can keep the questions coming, and perhaps after the session attend to some of the many other fascinating inquiries that have arisen. Thank you, Jim. Sumitomo Electric are one of the IFBF's platinum sponsors. Toshikazu Shibata is General Manager of the Flow Battery Engineering Department of Energy at Sumitomo Electric Industries. He's currently working on the development of flow battery systems and was previously engaged in the research and development of large capacity power cables. He's also a member of the IEC Committee and Working Group on Flow Battery Standards, IEC TC21 at JWG7. You may remember we heard about Sumitomo's flow battery in Belgium yesterday. I've invited Shibata-san to talk to us about two of the large Sumitomo flow battery projects, one in Hokkaido and one in California. He's talking to us live from Japan. I'm not sure whether to say Ohio gozaimasu or konbanwa, but anyway, welcome. Please turn on your microphone and over to you.
Good evening. Thank you very much, Mr. Anthony, for your kind introduction. I thought I couldn't meet the flow battery guys at this time of this year because of the COVID-19 pandemic issue. So I'm happy to meet you and to be able to give a presentation this year. I thanks to the secretaries who organized IFBF showcase. Today, I will talk about our experience of large-scale flow battery installation. At first, I introduced our flow battery development history. We Sumitomo started R&D of flow battery in 1980s. At first, we were developing an iron chromium flow battery. In the 1990s, the target of development was changed to vanadium because of that high energy density and using the same active material, both positive and negative, and the solvent is sulfuric acid instead of hydrochloric acid. In 2000, we commercialized the vanadium flow battery systems and started the business. The famous Tomama systems for wind turbines was installed at this time. However, the high price of vanadium caused us to suspend our business for a period of time. During this time, we focused on the development of cell stacks and developed highly reliable cell stacks with extremely low electrolyte leakage risk. In addition, we took measures against troubles that occurred in about 20 systems that had been installed so far, and we restarted business in 2012. Today, I will introduce the recently installed equipment, including operation data examples. Next page, please. Next page, please. Okay. I already introduced the energy storage use case in this picture. Previous page, please. Sorry. I always introduced the energy use case using this picture. Electric power is generated, transmitted, and distributed and consumed. The need for energy storage equipment are in these various scenes. Most needs 20 years ago were pitch cut systems for factory or offices. In that time, when there was real solar power generation, so the electric bill at night was lower than that at daytime. And there was a merit by charging at night and discharging at daytime. After that, with the expansion of installing wind power generation and solar power, grid frequency problems due to output fluctuation occurred. Therefore, there was need for storage batteries that smooth output fluctuation in a short cycle. Further, now, due to the explosive introduction of solar power generation, the use of surplus power during the daytime at another time by using a storage battery has also needed. On the other hand, if the IPP of wind or solar power owns the storage battery, there's a problem that the profitability of the business can't be established. So the following mechanism or scheme was established. One is the method of buying and selling energy on the market principle and procuring adjustment power. The other is a method that the electric power company owns the storage batteries and uses it in the same way as the output adjustment of hydro plant or summer plant. Recently, we are paying attention to microgrid use case. The aim is to improve the resiliency against disasters such as wildfires in the United States or typhoon or earthquakes in Japan. Next page, please. We have installed about 30 systems so far, and the total installed capacity has exceeded 100 megawatt-hour. Today, I will introduce 3 systems. Next page, please. The first to introduce is the world's largest flow battery system. A 16 megawatt-hour vanadium flow battery system was installed in the Minami Hayakita substation of Hokkaido Electric Power Company. It took 2 years to build. In the first year, we do civil work, and the second year, we install systems and perform commissioning the test. The system started operation in December 2015, and the 3-year demonstration program was completed. The results of each verification were introduced 3 times at IFBF. And from December 2018, this system is used as a commercial power source for frequency adjustment in the Hokkaido area. Next page, please. Using this system, the battery itself and the various control methods were evaluated. I show representative data. As for control method evaluation, high-speed response was evaluated, and flowability to a very fast command was evaluated. The graph on the upper left is an example of governor-free operation. The upper picture shows the grid frequency, and the lower picture shows the battery output. In this operation, charging/discharging is performed to cancel the frequency deviation. If you look closely, you can see that the frequency deviation is reduced by controlling the storage batteries. The figure on the right shows the results of the capacity tests conducted each year. The system consists of 13 banks. No significant deterioration has been observed in any of the banks. And linear approximation from the yearly capacity measurements data shows a slightly decrease in capacity per year. The system keeps rated capacity for 20 years. And there's no need to replace the cell stacks through. Also, there were few troubles during the 3-year demonstration period, and the 3-year availability was 97.3%. And 18 months have passed since starting the commercial operation. In this period, there's no trouble, and the availability is 100%. Next page, please. Next is a system installed in California. The capacity is 8 megawatt-hour, and it is for KAIS operation. KAIS is a California Independent System Operator. This system trades electricity in the KAIS market. This project is promoted by NEDO. NEDO is a new energy and industrial technology development organization. We started operation in March 2017. This system is only flow battery system trading in the KAIS market. Next page, please. This is an example of KAIS operation. Red dashed line is output command, and black line is the output of battery system. As this picture shows, very good flowability can be confirmed. It's possible to operate for both long cycle energy command and short cycle ancillary service command. And it is also possible to respond to commands superimposed with them. In addition, lower graph, it shows a SOC. It can operate in the entire full range of SOC, which is the merit of flow batteries that are not limited by the number of cycles. Next page, please. Next is microgrid use. It is installed in Morocco for Massen. This is small demonstration system. Capacity is only 500 kilowatt-hour. Next page, please. This system is connected to PV, and this is an example of microgrid operation. In this microgrid, flow battery take a role of voltage source of the microgrid. In the graph, the green line shows the PV output, and the red line shows the flow battery output. The connected load is 20 kilowatts, and the blue line is total output of PV and the battery. The blue line can be maintained at 20 kilowatts, which is the same as the load, by adjusting the output by the flow battery according to the output of PVs. Okay, the next page, please. This is lithium-ion battery and the flow batteries comparison. As for capex, battery cost is, I think, lower. DB is lower than flow battery, but flow battery cost lower in long duration use, and the management cost is high. So DB is lower than flow battery. And as for construction, flow battery is chemical works. So REB is lower than flow battery. As for OPEX, but REB needs a replace. On the other hand, life of flow battery is more than 20 years. So as for OPEX, flow battery is lower than REB. And as for removal cost, lithium-ion has a high industrial disposal cost. On the other hand, vanadium electrode can be reused or recycled. So I think removal cost of flow battery is lower than REB. And as for performance, generally, as for efficiency and energy density, REB is better than flow battery. However, the deterioration rate of REB is generally faster than that of flow battery. So this performance depends on the operation periods.
And as for safety, many cases of refire incident have been reported. So both Liyu and flow battery have advantage and disadvantage, and which battery is selected is according to the application, operation period, and customer's policy. In most cases, low-price battery systems are selected. Here, I think life cycle cost is very important. In CapEx, especially short duration system, Liyu is cheaper. But in consideration of OPEX and removal cost, flow battery have many chance in some cases, I think. Next page, please. Next page, please. Okay, thank you. This is our, sorry, previous slide. Oh, thank you. This is our next project. Sumitomo's flow battery won new energy storage system bid. In this tender, a total cost of CapEx, OPEX, and removal costs are evaluated, regardless of the type of storage battery. The construction of the large-scale flow battery system will begin soon. That's all. Thank you for your attention.
Shibata-san, thank you very much. That was great. Clearly, there's a little bit of latency with the slides arranging. Andy, if you're there, would you like to pick a question, please, for Mr. Shibata from the submitted list?
Yeah, sure. So we've got a couple of good questions. One question is, how many megawatt hours have Sumitomo deployed in total with flow batteries? And also, what is the longest operating time that you have had a battery in the field?
Sorry, pardon? Yeah.
Right. So the question was, what's the total number of megawatt hours that Sumitomo have deployed? And also, because you've been deploying megawatt scale flow batteries longer than anyone else, what is the longest operational time for a fielded unit in the your flow batteries, please?
In your experience, the longest operation period years operation 2000 to 2010 for 10 years. This is one case, about 500 kilowatt system. Now that system is removed. Okay. And the cycle number is about 3,000 cycle, because 1 year, one cycle per day, and okay. The operation is 10 years, so about 3,600 cycle. The longest period is. Yes, okay.
So that sounds to us to be a very important data point. Can I just confirm, you said that the longest time a unit has been operating is 14 years? Did I hear that correctly?
Or 14?
Yeah.
Yeah, no, our longest is 10 years.
10 years.
Our
10 years.
10 years.
Okay. That is still a very, very good.
Design is in our design, life cycle is more than 20 years.
Thank you.
In our design.
All right. Thank you very much indeed. That's some wonderful good news stories about the number of large installations and the deployed base of flow batteries around the world. Thank you very much, and good night in Japan.
Yeah.
We now end our session and we move on to 3 speakers who will each be talking about their company's proprietary flow battery system. First, we will hear from Wiebrand Kout, who's CTO and founder of Elestor. Wiebrand has worked on 2 separate hydrogen electrical chemical systems before starting with Elestor in 2014. with his aim to bring large-scale, very low-cost flow batteries to the market. At Elestor, Wiebrand is responsible for the development of his company's core technology, intellectual property, the cost modelling and product planning. Welcome, Wiebrand. Please turn on your microphone and over to you.
Good afternoon. I hope my microphone is on already.
You're working, thank you.
Excellent. It's an absolute pleasure for me to be talking to all of you. Would have loved to be in Düsseldorf, close to home, but we ended up a bit closer to home even than I had hoped for. What I'll talk about in the next 10 minutes is a project called Melody that we started to develop for the first time ever, a membrane-less flow battery stack. So on the next slide, please. Just a few words to explain why. I've been in the flow battery business now for 6 years, and I can tell you that nobody really cares about flow batteries. What people care about is cost of storage. And in the past few years, it's also illustrated in the graph, we've seen an amazing cost reduction in lithium happening. So they have economies of scale that a flow battery does not have yet. Still, the only justification to do any flow battery research at all is the possibility to undercut the cost level of lithium. And so what I've mentioned here, not system prices, cell prices right now at about 110 euros per kilowatt hour. By the mid of this decade, this will be reduced to 75 euros per kilowatt hour. It's ever so easy to underestimate this cost reduction. Don't do it if you want to succeed with flow batteries. So ever since I founded Elestor, we've been pushing to a number of 50 euros per megawatt hour cycle. So the cost of charging, discharging per megawatt hour, levelized cost of storage. So what you can also see in the graph, that's even with the impressive cost reduction in lithium cells, still it's a challenge to be even near 100 euros per megawatt hour cycle. So there is still a lot of room for improvement, and it is, I'm absolutely convinced, possible to beat lithium on the one point that customers do care about, cost. So low capex and long lifetime. So on the next slide, a few words on how we will do this within the Melody project. First of all, we cut off everything that doesn't really have to be there to fulfill the goal of storing electricity. So if you look at, for example, vanadium flow batteries, there the membrane can be quite significant as a cost driver. Our flow battery type, the hydrogen bromine chemistry, is special in that it is a gas and liquid battery. This has the advantage that the gas and the liquids won't mix. So this opens really interesting opportunities. For example, you can operate a hydrogen bromine cell without any membrane. This is something that was already explained at IFBF in 2015 by William Braff, who also had a publication in Nature with really exciting single cell pioneering work he did back then. The way it works, we have hydrogen on the one side. So in the picture, that's the anode. We have a mixture of hydrogen bromide, bromine, tribromide on the other side. And then instead of having a membrane, we simply use hydrogen bromide, which costs next to nothing and is about 10 times more proton conductive than the expensive PFSA membranes that it replaces. But what we are doing then is having two liquid streams floating above each other. So it's a key challenge to not have them mix. Something that has been pioneered at Technion in Israel is to use a dispersion blocker to keep the two liquids from mixing. Single cells exist, but no team has ever succeeded in turning this into a working stack with a large active area. And this is exactly what we will do within the Melody project. The low, you guessed it, is low cost. The electrolyte, well, using hydrogen bromide as the active material opens the opportunity to really low cost electrolytes, so less than 25 euros per kilowatt hour, including costs for complexing agents, is definitely possible. And also, since we have taken out a big source of resistance, the membrane, we can get really interesting high kilowatts per meter square, which simply is cost reduction because we have less cells to get the power we want. Another way to reduce cost, reduce the volume. It's less material, as simple as that. We can get, with the right complexing agent additives, over 300 watt-hours per liter for the liquid. Energy density of the hydrogen gas, of course, is influenced by the hydrogen pressure. Within the project, we will go to 200 bar, which may sound high, but this is a perfectly normal industrial gas pressure. And everybody knows that in automotive fuel cells, 700 bar is the standard. Also, because the gas and the liquid just won't mix, it is possible to put everything in one tank, which really simplifies the entire system. So we have only one tank instead of two, and we can do away with a lot of piping, valving, and what else. Elestor is not the only company doing this. Really fortunate to have a strong consortium to work on this challenge. They're shown on the next slide. So we have a really good team of universities and research institutes and industry. So there's Delft University who will work with us on the cell design. There will be a lot of fluids analysis, managing the flows to get the good Coulombic efficiency. The electrodes, the catalysts, are a massive challenge. Also in the, let's say, regular hydrogen bromine flow battery with a membrane. But we are increasing the challenge by taking out this membrane. So really glad that we have the University of Exeter, ETH Zurich, and PV3, who will all work on the electrode and catalyst. The technology leader today, I believe, in membrane-less electrochemical cells is Technion from Israel. So they are bringing in their know-how. That was shown on the previous slide is a membrane-less cell, large area cell that's working as we speak at Technion. Elestor will take their design, scale it up. So we're aiming for a over 600 square centimeter cell area. And we will put that into a system using the system building know-how of Shell. Who you all know, maybe not necessarily as a flow battery company, but obviously they're very good at building very large installations with a very high level of safety. Finally, recycling, important topic in flow batteries, and something that is probably an advantage versus lithium-ion. To live up to this claim, Vertech of France will do the complete life cycle analysis of the technology that we are developing. It's a 4-year project. We started in January. We did not have quite the start that we wanted because of COVID. But yeah, we have working cells. The first materials are working in the labs of the partners. So despite COVID, it's actually looking really good. There will be regular updates over the next few years on melodyproject.eu. So please watch that space. And please go to the next slide. So it's all about winning the race to the bottom. The drive to reduce the cost for electricity storage will never, ever go away. So obviously you need to get the round trip efficiency right. 70% of the electric energy that you put in has to come out at least. 10,000 cycles, sure. Long duration, also. By the way, what you will also see, especially with the solar coupled systems, is that the charge time is far shorter than the discharge. Good news is that most flow battery chemistries can actually do this. However, the real challenge, so if you could hit enter, please. The real challenge is to bring down the capital expenses to below 80 euros per kilowatt hour. And here I'm not comparing to lithium-ion cells. Here I'm talking about as installed, ready for use storage systems, including the inverter, including everything. Here, if you want to get the 50 euros per megawatt hour cycle, 80 euros per kilowatt hour installed capex is the upper limit, because there has to be room for energy losses, and also the project developer has to make some money. And finally, we must decarbonize the worldwide electricity supply within the next 30 years. To actually do that, I think at least 500 terawatt hours of storage capacity will be needed. So whatever material you choose, it has to be able to go the distance. The market for storage will not be saturated until we reach the 500 terawatt hours. And this is the really, really good point about using the hydrogen bromide as your active material. So low capex and very high scalability. This is what the challenge is. And this is exactly what we will do within the Melody project. And this brings me to the end of my presentation. Thank you very much for your attention.
Thank you very much, Wiebrand. Andy, can we go straight over to you for some questions, please?
Yeah, sure. So I've had a couple of questions asking you to just talk a little about the safety issues of using bromine and hydrogen.
Yes, I've been using hydrogen for 20 years, working with the bromine cells for 6 years. It's neither are for beginners. As you have to know what you're working with. But it's, and this is what we know for sure, it is possible to make this into a very highly safe system. I believe it is safer compared to lithium because of its predictability. And we can predict what will happen in case of a failure, and then we can design for graceful failure. So it's actually a really good opportunity to build intellectual property on how to do this with a very high safety standard. Thank you.
Andy, another question? I think we have time.
Yeah, sure. So another one was regarding catalysts and the need for a catalyst and issues with that.
Yes, there are issues with the catalyst. It's a big challenge to get a catalyst, especially the one on the hydrogen side, that can do both the charging and the discharging operation and won't corrode because of the inevitable bromine crossover. So here we found a solution that works, and we can have cells operating for months on end without measurable degradation. The Melody concept is special. We take out the membrane. So here you need to be very careful to pressure balance everything to keep the catalyst from flooding. On the other hand, this continuous stream of hydrogen bromide that we now have is also doing a really good job at scavenging any bromine molecules that are trying to make their way to the catalyst side. So based on the pioneering work done by Technion, actually this was a positive surprise to me. It seems like it's actually more catalyst friendly and not less. But even with the conventional cells, which do contain a membrane, we know we can get the lifetime we need.
Super. Thank you very much indeed, Wiebrand.
My pleasure.
We must move on. Next we hear from Liyu Li. After working at Pacific Northwest National Laboratory and co-founding Uni Energy Technologies, sometimes known as UET, Liyu has now gone on to found Creek Channel, where he is working on iron chromium flow battery systems. So welcome, Liyu. Please turn on your microphone and over to you.
Hello. Hi. Thank you, Anthony. So my microphone works fine.
Please go ahead.
Good. Okay. So in the past couple of years, I've been working on some low-cost flow battery systems, mostly for long duration energy storage. Next slide, please. Back in late 2015, Mr. Bill Gates made a comment on this on the redox flow battery system. I believe most of the audience here already read about these comments. He said Gates said the flow battery would last longer and store more energy than today's battery, but there's still one challenge. He says many are working prototypes using vanadium, a relatively rare element, as the active electrolyte. So the future system will need to use more easily available electrolyte before they can commercially feasible. So with this comment, I think we need to explore some kind of low-cost system with some practical applications. Next slide, please. So the first system invented for the true redox flow battery system was this one, the iron chrome system, that was developed by Dr. Lawrence Fowler at NASA. In this system, he used iron 2 and iron 3 on one side, and chrome 2 and chrome 3 on the other side, and using hydrogen chloride as supporting electrolyte. So this system was evaluated among other systems in the in their early work back in 1970s, 1980s, and eventually they pick up this system, the iron chrome system, not only because this system has a very good electrochemical performance, but also have a major advantage, which is very important for today's work. Next slide, please. So this system uses Earth's abundant and high production capacity material as their energy storage media. So this system uses iron, hydrogen chloride acid, and chromium. So we all know for the large-scale energy storage, we need Earth's abundant material to support this application. So for this one, the iron and hydrochloride acid has a lot of capacities. The only thing is the chromium. The chromium production in 2018, we can equivalent of 1,400 gigawatt-hour capacity for each year. So which is about like more than about 100 times more than the vanadium production capacity. And theoretically, the raw material cost for all these three key elements for energy storage media can be less than $20 per kilowatt hour. So this advantage is very attractive, and also because the iron chrome system using very similar structure like the current the widely studied vanadium redox flow battery system. So the other infrastructure already there. So it's kind of like very attractive if we can make this thing work. So next slide, please. This system, many companies are working on this system before, since the Dr. Larry Soller reported this one, but unfortunately not very successful so far. I think they got many issues, many concerns. One of the major issues is the hydrogen generation in this system. The hydrogen generation from the negative electrode from the chromium 2 and chromium 3 is it's because it's a very low standard potential, close to the hydrogen generation potential. So always have a small amount of hydrogen generation during this operation. So although each cycle you have about like 1% or a little bit more than 1% capacity decay, but in the long run you're getting a pretty big capacity loss during the long-term energy storage operation. So this one, this is one of the issues, but among other issues also. So this one makes the system kind of like not very stable, not very practical for the long-term performance. There's many technologies that try to solve this issue, but it seems like none of them are very successful. So next slide, please. What we did at Creek Channel, we worked, try to see if we can minimize the hydrogen generation, and also we try to see if we can getting a very simple, straightforward capacity recovery technology to try to get the system stable. So we have developed two different major technologies. The first one is we can getting a very low hydrogen generation during this operation. We can get the hydrogen generation in terms of capacity loss per cycle less than 0.3% per cycle, which not only the system design, also the optimization of operation parameters. And also we have developed a very straightforward, simple capacity recovery technology, which can getting the any lost capacity back into the system. So that's what we developed so far. And the next slide, please. This one shows some data we got using a testing system with a kilowatt scale test stand. We use a kilowatt scale stack and using about 100 liter electrolyte. We operated the system for total about 1,000 cycles. At the beginning, if you see the left-hand side, the Formula A, we found that we can get a stable performance, but the capacity energy density seems pretty low. It's only about 5 watt-hour per liter. And then we kind of adjust the formula to a new one, and then we can get in the energy density about 10. So also, if you can see the right-hand side, with some kind of operation optimization, we can get in the energy density more than 12 watt-hour per liter. And also, we can successfully keep the steady performance for more than like 500 cycles. The efficiency, Coulomb efficiency, also very stable, about like 95%. So seems like it's possible we can get in this system operating in reasonable performance and also relatively stable stable performance also. So with this one, next slide, please. We are working on some kind of prototype products right now, try to put the kind of this system into a standard ISO container and try to get in about 10 hour or maybe 12 hours product. So the rated power based on what we achieved so far can be 25 kilowatt, and the full capacity can be 250 kilowatt hour. So this one, because we use this the iron chrome system, and also because the iron chrome system, the iron 2 and iron 3, the oxidation power is not very strong. We can use a much lower cost membrane, not using the lithium membrane. We can using some kind of hydrocarbon based iron exchanger or separator, so the whole cost can be largely reduced. So for more than 10 hours of product, and with kind of industry scale production, so we think the initial cost for this system can be less than $100 per kilowatt hour, and the levelized cost of energy storage can be less than 2 cents per kilowatt hour. So this one we can use a lot of experience from the previous company's operation, and also from the vanadium company's operation. So we can use their production line, also can use their supply chain to getting the cost down quickly. So with this one, next slide, please. We also now noticed recently the clean energy production costs from wind and PV kind of getting down very, very quickly. So with this low cost energy storage products, we believe the renewables can be cheaper than most grid power electricity we have right now on in the market. Next slide, please. So with that, I thank you for your attention, and I'd like to see if you have any questions or any comments.
Liyu, thank you very much. Liyu, Andy, do we have some questions for Liyu, please?
Yes, we do. We have one question about the life of the membrane. What kind of life would you get out of the membrane in this battery?
Yeah, the membrane depends on what type of the membrane you use. So we are evaluating many membranes right now. So if we are using the hydrocarbon-based membrane, I believe based on the previous company's experience, should be around 5 years. It's also depend on the operation condition. So if you're using other separators, the lifetime may be changed differently.
Thank you. And Andy, I think we have time for one more question, please.
Okay, there's also a couple of questions regarding energy density, and particularly, do you see an opportunity to increase beyond 10-12 watt-hours per liter with this chemistry?
Yeah, that's a good question. I think it's quite possible we can improve that one. Right now, the utilization of the active material is only we still have a big margin over there. So we predict increasing another 20-30% of that energy density. That's possible. We can get in 15 watt-hour per liter, which is achievable in terms of in the near future.
Liyu, thank you very much indeed for your contribution this afternoon. It's fascinating to see the technology re-emerge, and I know that there are many people in the audience watching who've got a long history with the iron chrome system, and in particular, I hope that Larry is also listening in, and may we thank him for his support for the IFBF over the years as well. Thank you. Our final speaker today is Dr. Tim von Werne, CEO of RFC Power. RFC Power is a spin-out from Imperial College in London, which is developing a new low-cost hybrid flow battery. Tim is a chemist and has 20 years experience working with early stage technology startups, helping to turn cutting edge science into valuable products and services. Tim, welcome. Please turn on your microphone and over to you.
Excellent, Anthony. Thank you for the introduction and for the invitation to give a brief talk here at the showcase. And thanks a lot again for pulling this together at relatively short notice, as the opportunity to meet in person sort of has gone away. I do also realize that this is the last talk of the day, so I appreciate that people have stuck around, and hopefully I can keep you engaged for sort of the next few minutes as I talk about the technology we're developing at RFC Power. So Anthony, you sort of asked me to give a brief talk about the sort of some of the motivations for the work that we're doing at RFC. Then give an introduction to the technology and the system that we're developing, and then lastly, maybe give you an idea as to how and when we might be actually impacting the industry, when we might get a product to market. So if we go to the next slide, and I will start with the motivation. Obviously, everyone here today is here because we believe that energy storage has a big role to play in the transition to a low carbon energy system, and in particular the role that flow batteries have to play in the long duration energy storage. But we've heard multiple times today, yesterday, previous flow battery forums, that one of the real issues that's preventing the widespread adoption is cost. And as with I think the development of all of the other chemistries that have been presented at this showcase and at the previous forums, the primary motivation and primary driver is to see what we can do to bring down that cost. Actually, Mikhail's from Bushveld Energy had a good slide in his talk yesterday that sort of addressed where the key points for getting cost out of the system might be. And obviously, the biggest is and probably the most obvious is in the electrolyte cost. So that's what we've been doing at RFC Power, is to look at what we can do to bring down the electrolyte cost and really the overall cost of materials to make these systems more financially viable. So if we go to the next slide. So the solution that we developed at RFC Power is the manganese hydrogen hybrid flow battery. And this solution really addresses the cost issue through two fundamental ways. Firstly, by moving from a liquid-liquid flow battery into a liquid-gas hybrid architecture, you immediately cut the volume of electrolyte required in half. And where a huge cost of the system is in the electrolyte, that in and of itself offers potential for significant cost savings. Obviously, the hydrogen is involved, but you actually get the hydrogen for free as you're running the system. The hybrid configuration also offers some other benefits. Obviously, because you no longer have the risk of your active elements or risk of cross-contamination due to crossover through the membrane, that allows you to potentially bring down the cost of your membrane materials. But also it means that you no longer need to use the same redox metal on both sides of your system. And that really drives the second technology innovation and second cost reduction in our system. We're moving away from vanadium to a much lower cost material, and the electrolyte we're using is based on manganese. Manganese is obviously a low cost. Oh, sorry, if you could go back first, please. Almost there. Thank you. Yeah, so manganese is a low-cost material. It's extremely abundant. I think it's the 12th most abundant material in the Earth's crust. It's mined extensively, sort of across the globe. Manganese is already widely used in energy storage in batteries. It's in the ubiquitous sort of alkaline disposable battery. Those use quite a bit of manganese. But also the commodity prices of manganese are much more stable, and they haven't been subject to the same sort of volatility that you see in the vanadium space. So what you get from this is obviously that manganese is a low cost material. Because the manganese is not involved in the reaction at the electrode, stays in the solution, we can maintain the full energy and power decoupling. That is sort of one of the hallmarks, one of the advantages of flow batteries. Again, I mentioned the hybrid system prevents crossover of active species, causing problems with capacity loss. If there is any crossover, it can be simply pumped back into the electrolyte system. And the result of all of this really is that we should be able to get a substantial reduction in the upfront cost of the system. If you go to the next slide, please. So the chemistry of our system is relatively simple, is laid out here. So during charge, we are oxidizing the manganese 2 plus to manganese 3. The proton from the acidic solution of the acidic electrolyte solution migrates across the membrane and forms hydrogen. Hydrogen is captured and compressed and stored locally. Discharge, hydrogen is consumed, and manganese 3 is then reduced back down to manganese 2. And the advantages of using this chemistry are that the manganese 2-3 couple has a high redox potential, so 1.5 volts. Which means that we get a very good cell voltage. And manganese also has a very good solubility. So we're working at an energy density upwards of 30, approaching 35 watt-hours per liter for the electrolyte. But the electrolyte formulation also is not corrosive to the catalyst. What that means is if there is any crossover of the electrolyte through the membrane, we've yet to observe any reduction in the catalyst activity for the hydrogen side, which means that we have the scope to reduce the amount of catalyst that we're adding to the system, help us bring costs down, and potentially use thinner, cheaper membranes. And again, if materials coming across, just pump it back through. So we're regularly getting energy efficiencies greater than 75%. We've seen up to 85% in an optimized performance on a small cell. Again, all of this drives reduced cost and the potential for really having a very low cost energy storage system. We go to the next slide. Finally, the last thing for me, I suppose, would be on the industry engagement and how and when we might impact. Will there be a hydrogen manganese flow battery at the gigawatt scale in a couple months' time? I don't think so. We're still very early stage in the development process, and our core expertise is in the chemistry, and we're building now the cell and stack design expertise. That said, we don't really want to be another flow battery manufacturer. There's been a lot of companies who spent a lot of time to build the expertise in sort of system design, system engineering to build these systems and bring them to market. We'd like to partner wherever possible with those companies to help potentially reduce their costs and see if there's a way to get this technology to market faster. And hopefully bring something to that can have an impact on energy storage prices before lithium-ion prices continue to drop. If you go to the next slide, and this is the very last for me. Finally, just to give you an idea of where we've come from. So Anthony mentioned that we are a spin-out from Imperial College London. So we are commercializing work that was done in the labs of Nigel Brand and Anthony Christianak at Imperial in the engineering and chemistry departments. They both have a long history in electrochemistry and fuel cells and flow batteries. We've recently built out the team here within RFC to include some more people with industrial experience in flow batteries. You may recognize a few of those. The eagle-eyed among you might recognize Ashkan Kave, who gave a poster pitch at last year's Flow Battery Forum in Lyon. And yeah, that will be it for me. So if we just go to the last slide, I will say thank you, Anthony, again for the introduction, the opportunity to present. Hoping that we can come and give a more detailed presentation with some more data in it at the next meeting in Düsseldorf. With that, I'll take any questions if you have them.
Tim, thank you very much for your contribution. That's great. And it's good to see your team, some very familiar faces from the whole world of flow batteries, including your latest edition, Phil. So that's nice to see and welcome. Andy, I'm sure we got some questions and we have time for a couple, please.
Great. So I'll just run off a couple. There's one that's probably a quick one, which is what is the PhD of the pH? Sorry, what is the pH of the electrolyte? And also, do you need an electrolyte on the H2 side?
Okay, I can answer this relatively quickly. The electrolyte is quite acidic. I don't know the pH offhand, but it is going to be quite low. You know, I wouldn't expect it to be much above 1. So it is sulfuric acid based electrolyte. And the answer to the other, do we need an electrolyte on the hydrogen side? No, we don't. The hydrogen is evolved directly off the surface of the electrode.
Thank you. Andy, any more?
Yeah, there's one here that will certainly test my chemistry. So there's a question that the manganese 3+ is disproportionate to the manganese O2. How do you control it?
Yes, that is a very good chemistry question. And one of the problems with manganese, historically has been that manganese 3 does have a tendency to disproportionate, and so manganese 2, manganese 3 will react and create another manganese 2+ and a manganese dioxide, which is insoluble and crashes out. So we do add stabilizers, electrolyte, which prevent that disproportionation and irreversible capacity loss. And we've run hundreds of cycles on the cells that we're doing and have done that without any capacity loss. So it's something that we believe is fully functional. Obviously, we need to still scale that and show that over thousands of cycles. But we've not been worried by anything we've seen yet.
Super. Thank you very much. And I think there's time for just one final question, if there's one there, Andy, please.
Sure. So, does RFC have patents or patents pending on this system?
We do, yes. So there's been a number of patents that have been filed to cover the core technology. So there were 3 patents in the original portfolio. All 3 of those have been granted now in sort of multiple territories. There's been several additional filings since then, and we'd look to expand our IP portfolio as we further develop the technology and generate more IP, particularly in the sort of electrolyte chemistry, cell and stack design areas.
Tim, thank you very much for your contribution. Thank you. This showcase would not have been possible without the support of our sponsors, especially our platinum sponsors today, Solvay and Sumitomo. Our host for this event has been GemServe, and I thank renewable energy aggregators who facilitated much of yesterday's discussion. But thank you all to all of our speakers, not only in today's sessions, but also those who spoke to us yesterday.